trigonometry. Today is the first lesson of the next chapter, but if you're confused as I go along and go, couldn't this just be in the chapter we're doing? Yeah, and some of it we've already seen before. To show it to you though, I'm not going to start here. I'm going to write some sentences in a second, but I'm going to go over to Desmos, and I encourage you to get Desmos on your phone for a lot of the stuff we're going to do in this chapter. We're going to try and find out more about the graphs. Okay? So I put up y equals x squared. My only question is today, what if I put a number out front? We've been calling that the a value. What happens to the graph when I put an a value up front? And Desmos is really good at this. If I go up and change it to y equals 2x squared, I think I can teach most of the lesson just by looking at y equals 2x squared. I can tell you most of what is going on just by looking at y equals x squared and y equals 2x squared. And Desmos has awesome stretch or awesome zoom features. I just rolled in with my mouse, but you can do it with your fingers on a touch screen. Very quickly you can see, and color-coded too. So y equals x squared is the red one, y equals 2x squared is the blue one. And here it comes. Maybe the whole lesson in one sentence. When I take the parabola y equals x squared and I multiply it by 2, all the y values double, and the effect is a vertical stretch, almost like somebody grabbed the top of this thing and pulled it upwards to the new parabola by a factor 2. Well, and what I mean by that is, let's really look right here. I'm going to put 2 points on there, and Desmos is great at this too. I'm going to click on 2 points here, right down here, this one, and it'll show the label for me if I do it just right. No, it's not holding it. So I will label the points myself. 1, 1. On the first parabola is the point 1, 1. And then on the other parabola, it's 1, 2. And when you look at that, hopefully you're like, yeah, 1, 1, and 1, 2. Let me really zoom in on that. If it was a 1 on the red parabola and I multiplied it by 2, now it's a 2 on the other parabola. Well, better yet, let's do one more point. Not to belabor it, but one more point here. 2, 4 is on the first parabola. And so on the other parabola, it's 2, 8 because the y value got doubled. You see it there, 2, 8. I'm going to label it. That's what's going on. Okay? So now, Desmos does all sorts of other cool stuff. Like if that's y equals 2x squared, I'm going to put up y equals 3x squared, and I hope you're not blown away by this. I hope this is like, yeah, I see that. See? It's just stretched up even farther. I'll turn off 2x squared for a second so you can see 3x squared. It's just stretched by factor 3. So the only other question is, what happens if I don't use 2 or 3 or 4? What if I use like a fraction? I don't know, can you predict what's going to happen if I do half of x squared? What's it going to look like? What's that? Oh, okay. Let's jump ahead and do that. Let's do negatives, because we saw those before actually. What if I did negative x squared? Do you see what happens with a negative? All the y values become negative, and it's just flipped over, right? Well, let's go back to the fractions though. If I put a fraction out front of this thing, what do you expect you're going to see compared to the regular y equals x squared? I'll turn that one off. There's y equals x squared. I'm going to do y equals half of x squared. And then turn it on. You see? Yeah, it gets bigger. And this is the only real difficulty in the whole thing is it's like, okay, what happened to it? What really happened to it is I made the y values half. I crunched it down. But you might look at it and go, well, it's wider. Those two things are sort of interchangeable. And you think about if I grabbed an elastic band and I stretched it this way, upwards, it would look like it was compressing horizontally. So I know those two things sort of intertwine there. So we're going to have to deal with that somewhere along the way. For now, we'll just call it all vertical stretches and just leave it at that. Well, I hope it's not too big a jump now to jump back to the lesson and actually move pretty quickly, I think. When compared to y equals x squared, the graph of y equals ax squared is a parabola that is either vertically stretched or compressed. That's the whole story right there. I mean, if you watched what happened on Desmos and you saw that, that might be the end of it.
If you put like a really small fraction there, like 1 over 100 or 1 over 1,000, is it going to eventually like stretch out until it's like...
Yeah, it looks almost flat. But it will never be totally flat. And I can sort of defeat Desmos on one screen, but if I zoom, so let's go 1 over, I'll go big, 1,000. See, it looks like a straight line. That's how small it is. But if you go out, it is a parabola. See, eventually it does start coming upwards. And eventually, if you go out far enough, it will go all the way back up again. It just takes a long time to do that, okay? Good question. Okay, now this is a package, yes? There you go. There's my pen. So when a is greater than 1, like 2 or 3 or 4, so put that on there above the a equals 1, like numbers like 2, 3, 4. You know, you're talking about numbers that are bigger than 1. These are the numbers that will stretch it because multiplying by numbers bigger than 1 makes things bigger. So when a is greater than 1, the parabola is vertically stretched. But if a happens to be between 0 and 1, like if you're multiplying by one of those fractions, and again, if that looks confusing when it says 0 is less than a less than 1, that's confusing. Okay? We're talking about, like, let's say it's a half, or a third, or 2/5, some fraction that makes things smaller. I'm not trying to confuse it with the crazy letters there. When you're multiplying by a fraction, then the parabola is vertically compressed. And I know when you look at it, it looks like it's wider. Well, yeah, that's true. When you vertically compress something, then it looks wider. Think about stepping on something. You push it downwards, and as you do it, it becomes wider. Like, say, an orange or something like that. Let's say there's an orange on the ground, and you went and you stepped on it. You'd be compressing it, but that would make it wider at the same time, yes? Not a perfect comparison, but close. And what about what happened when a was negative?
Inverted.
It's inverted. Oh, I like that. I'm going to use that. When a is negative, the parabola inverts. You'll see it sometimes called vertically reflected. Okay? Give you time to copy that, but I want to keep it moving because I want to respect your time. Because I hope after what I've done, the next table will be, we'll just zip right through. We're like, okay, we know exactly what to do there. More time? More time? Yeah. Look, that volume question from yesterday is still on the board there. Look at that. Nobody dared to erase it. Oh, there's no one right beside it. Somebody did another volume one right beside it. Maybe at the math help room. They had one of those volume ones. I see people already filling in the table underneath. I hope that's true. I hope you can look at that table and go, oh, I already know what this table's asking me. It's just examples of what we did. So if you're waiting, maybe take a look and see if you can take a few guesses at those. That way, maybe we can do that next table fairly quickly. Good, time-wise, we're okay? What's going on out there? Watch this. Hey. I like that. Everybody's out there's like, okay. Okay, here's the table. Let's do them in columns. I think tables like this are fun in columns. It goes very quickly. Direction of opening, up or down. What does 3 do? Which way is it? This is up because the a is positive. We saw that before, didn't we? We already talked about that in another section. 0.5x squared, even though it's 0.5, it's still up because it's positive. And so both of these are down. And now you're ready for the glow dance. Yes, you got your move. You got parabola up, parabola down. Yeah, you won't be the only one, friends. You do that, there's going to be people in the room that go, yeah, I know what you're doing. Stretch or compress. Does 3 stretch things or compressing? If you multiply things by 3, do they get bigger or smaller? Stretch. Yeah, they get bigger, so that's a stretch. But what does 1/2 do to things? Does that stretch or compress them? That compresses them, because 0.5 makes things smaller. So maybe it's not about fractions. It's about whether this number out front makes things bigger or smaller. How about 2/5? Compress. So downwards but compressed. And then 7, stretch. Oops. Good. Shape of graph compared to y = x squared will be wider or narrower. So I'm a little scared to talk about this column, but it is true. So when you look at it, your brain might do this on you. 3x squared, stretched upwards, is it going to look wider or narrower? Narrower. It's going to look narrower. But you think about an elastic, right? If I took it and stretched it upwards, it's going to get narrower. Think about me. If someone grabbed my arms and pulled them straight up, things would get narrower. It would look narrower. But 0.5, because it's compressed, yes, this way, it's now going to look wider. And the same in reverse. When you're doing fractions, it's going to look wider when you're compressing, and it's going to look narrower when you're stretching. So I will mention that, even though we really want to focus on this column here, that's what we're going to use. I do mention, I know that visually this is what you'll see when you look at it. Yeah? How was that? Was that okay? Yeah. That's supposed to tie together with stuff you've already seen and go, yeah. We already sort of knew this. I didn't use these words, but yeah. So here's what we're going to do now. Make a table of values to graph this function y = 2x squared. All right, so to do each one of these, I'm going to go 2 times -3 squared. I'm doing it in my head. Maybe you'll do it in a calculator. -3 squared is 9. Times 2 is 18. Then I'm going to do it with -2. And last chapter, somebody came to me exasperated and said, do I have to build a table of values to graph a quadratic every time? And I said, for a little while, very soon. And it's right now. This example here, we'll be able to go, wait a minute, I've got something better now. We'll get something better right now. But I'll go through the whole table one more time, because you could do this if you were stuck on a homework question, like, oh, I don't know how to graph it, I don't know if it's right. You could just sub in numbers, you could do it. But we're going to come up with a shortcut in just a second here. Well, that's squared, but I don't care because it's 0. And this is 2 times 1 squared, 2 times 2 squared, which is 8, 2 times 3 squared, which is 18. And let's just rewind to the day where I told a lie. I said parabolas follow the 1, 3, 5 pattern. You can go, this doesn't follow 1, 3, 5. Look at it, it goes up 2, then 6, then 10. Who can explain that and make it so I'm not really lying?
It's a 1, 3, 5 pattern. It's a 1, 3, 5 pattern.
Yeah. Okay, so let me just graph these points and really narrow down this step pattern. Because I mentioned it before. We talked about it a little bit before, but now let's nail it down. So I go 0, 0, 1, 2, 2, 8, and 3, 18. And it's symmetrical, which is sort of nice when you're graphing these, because one side looks just like the other. So all that stuff's still true. It still has a low point like other parabolas did. Make a table of values and graph the function. Did it. Starting at the vertex, calculate the step pattern. So it goes up 2, then it goes up 6, then it goes up 10. Making Mr. Todd a liar. What do you notice from the original step pattern? It's doubled. And Chris has jumped to the grand conclusion already. I was sort of lying. What I should have said was parabolas follow a 1, 3, 5 pattern. If you want, they follow a 1a, 3a, 5a pattern. You always multiply by the a value. So someone jumps up and says, oh, I don't have to build a table of values anymore. I start with the vertex, and then I just use the step pattern 1a, 3a, 5a. Yes, we're well on our way to a great shortcut to graphing parabolas.
What's after 5a?
Yeah, 7a. Good. Let me add that. 7a, 9a, 11a. Why is that happening? Oh, more information to come on that. There's a specific reason why that happens with degree 2 functions. We're just not quite there yet. Right now we're in the observation stage. We're noticing it's happening, but the deep mathematical idea of why it's happening, still to come. Still to come. But maybe you already sort of knew that. Maybe we sort of talked about that, and that was already sort of out there for you. More time? Okay. So I'm going to do that one more time without the shortcut, and then we're going to just start using the shortcut. So I'm doing this very quickly to prove the exact same thing, because this is now negative 3x squared. So if I go negative 3 times negative 3 squared, I get negative 27. If I go negative 3 times negative 2 squared, I get negative 12. Negative 3 times negative 1 squared, I get negative 3. Negative 3 times 0 squared, I get 0. Negative 3 times 1 squared, negative 3. Mr. Todd, I thought we were done with building table values. Right. You're so right. And I just wanted to show it one more time to make sure you believe me about our shortcut. So I got 0, 0. I got negative 3 on both sides. I got negative 12 on both sides. And then I got negative 27. I didn't put the negative there. Negative 27 on both sides. And I did that quickly on purpose. I wasn't trying to, I actually am not trying to rush the lesson. I'm just trying to say that's not the important thing that's going on here now. And I look at the step pattern and I go, okay, this was down 3, and then down 9, and then down 15. And did our shortcut work? Was the step pattern 1a, 3a, 5a? Let's check. Here's what you'll do from now on. Well, we're done. Shortcut from now on. You'll go 1a, 3a, 5a. You'll write that down over here. And then you'll fill the a in, which is negative 3. You'll multiply them each by negative 3, and you'll get the step pattern you need. You'll draw the vertex, and then you won't go through all the table values and all the subbing. You'll just go down 3, down 9, down 15. Okay? I made a mistake there. I put negative 3a. I should have just put, I just meant to put negative 3. Whoa, giant eraser today. But maybe that was all sort of out there, was it? In the back of your mind, it was sort of like, I see where we're going with this. And today I'm just bringing it together. Handy for the test, too. If something comes up, you're like, you'll know this in the background. You really know about 1a, 3a, 5a if you have to use it tomorrow. I'm not sure you do have to use it. That wasn't a hint. That was just like, good to know. Yeah, it shouldn't mess you up. Is it good? Yeah, okay. I see people jumping ahead of the next question. Next question says, graph each parabola. So, we know it starts at 0, 0. All we're going to do now, instead of building the whole table of values, we're going to write down 1a, 3a, 5a to get the step pattern. Use the 1/2. So it's 1/2, 3 halves, 5 halves. And if you're fraction allergic in these situations, like, oh, this is going to mess me up, yeah, you can use the decimals. That's okay. 0.5, 1.5, 2.5. Now check this out. I put the vertex on. I go over 1, but I only go up 1/2. Then I go over 1, and from there, I go up 1.5. I added one word there that you'll need. From that point, then you go up. So from this point 2, then I go up, what was it, 2.5? There it is, 4.5. Does it look like a parabola? 1/2, 1.5, 2.5. Okay, so I did one with a fraction there. How about this one? 1a, 3a, oh, wait. I want to color code them so you can see. Go red here. 1a, 3a, 5a. But now it's negative 2 I'm multiplying by. So it's negative 2, negative 6, negative 10. Sort of giving away the open downwards thing, right? When the step pattern's negative, we're going downwards. So from there, you go down 2. From the vertex, you go down 2. From that point, then you go down 6. And this goes right off the page. You're like, I didn't need the negative 10. Well, it's nice to have the negative 10 so you know, yes. And then straight down from there. So negative 2. No, not straight down. Very down from there. There's that parabola. And graphing parabolas just got a lot easier. Yeah, bang the vertex on there. All we're going to do in the next few days after this is move that vertex around. We're going to see what does it take to move that vertex around. Question? It's supposed to be at negative 8 because from the negative 2, it's a step pattern. It's how do you go to the next one? Great question. Yeah, that's why I changed my phrasing slightly there. I said from there, negative 6. From there, down 6. From there, down 10. So the step is telling you what step to go, not what point to go to. Well, you know what's coming. The reverse question. Always in math, we do it one way, then we turn around and try and do it the other way. How about we don't do that, he says. I'm going to give you 2 parabolas. You got to figure out the step pattern. That's all. This one's opening downwards. Ooh, that one's hard. Let's do B first. B's easier. Yeah? Let's look at what happens with B. It went over 1, and then it went up 4. We're already home, right? We already know what's happening here because it was supposed to go up 1, but it went up 4. Well, let's just check the next point goes right off the screen. I can't even see it. I don't need another point. Over 1, up 4, that means it got multiplied by 4. This was y equals 4x squared. Okay? So sometimes the step patterns are easy. This one's not so easy because it's some kind of fraction. So we need somebody clever. I'll just write it, ax squared. Austin wants to be the clever person. Okay, I got a hint coming. So, well, get ready. If you don't say the right thing, then I'll give you a hint and you can change your answer. So either way, you're going to be right. Okay, Austin, what do you want to do?
So we're going to draw the connecting line, and then we write the fraction as rise over run.
Oh, yeah. See, you would get a good estimate. Somebody go, okay, like it's like 2/3 or something. You could estimate it. That is totally true. But if I wanted to get it exactly, here's my hint. You ready? There's an exact point. Sub it in, yeah? That's a skill we've really been working on, is subbing something in. So sometimes when it's a crazy fraction, go find a whole number and just sub that in. So I get negative 12 equals a times 2 squared. I think you'll calculate a to be negative. Oh, wait, something's wrong. Hold on. Oh, yeah, it's right. Therefore, y equals negative 3x squared. It wasn't a crazy fraction that caused the problem. It was a crazy scale. Do you see the scales? Like going by 4s? So I couldn't estimate it? Who would do that? Go by 4s? Well, sometimes we'll be forced to if the numbers are really get very big in a hurry, okay? So that sub and solve method, still out there if you need it. Questions? That was a little longer than I expected.